Hello, we would like to proudly introduce this year's Titan Rover, the Hephaestus. Titan Rover is a multidisciplinary team of students out of Fullerton, California, consisting of over 30 active members spanning between mechanical, computer, and electrical engineers, in collaboration with the computer science and biology departments.
To be more competitive in this year's URC competition, we have decided to completely redesign our Rover, starting with an overhaul of every single subsystem. By drastically reducing weight and upgrading integral subsystems, this year's Rover is leaner, meaner, and ready to compete.
The comms team is in charge of making sure that our base station and the Titan Rover are supplied with constant communication between each other. Each subsystem on the Rover will operate on the Titan Rover network, which will be supplied by an ASUS router. The purpose of the network is to have the base station computer and the Rover computer connected to each other to send and receive data through the antennas, so we can operate the Rover from afar. With this communication network, we can move the arm, perform tasks, and operate the motors on board.
This year, emphasis has been placed on shock absorbance, wheel alignment, and durability to ensure a reliable mobility system. The wheel consists primarily of 3D printed hardware, allowing us to manufacture critical components more quickly. The tire spoke geometry is designed to maintain a wide ground contact patch and absorb impacts caused by rough terrain, and angled tread has been added to optimize point turning.
This year, we will be dealing with a lithium-ion battery rated at 22.2 volts, which will be powering more than 5 components and require a lower voltage to operate. After considering this, we decided to implement a DC to DC converter that will be used to step down the voltage going directly to the TX2 board, as well as some buck converters to regulate the voltage going to the FPV cameras. To conclude the design, we will be integrating fuses into our circuit to protect the components in case there is an excessive amount of current. It blows the fuses instead of the components.
Returning in 2024 is the rocker bogie suspension system. This system, along with the differential bar mounted on top of the chassis, allows the Rover to ensure contact of all 6 wheels with the ground at all times and maintain chassis stability while traversing rugged terrains. All of the aluminum components have been fabricated in-house by the mobility team using CNC mill and lathe, water jet, and welding. ANSYS was used to analyze the structural integrity and performance of components and their assemblies by simulating how they respond to various forces. Each suspension assembly weighs just over 2 kilograms with a maximum tilt of 40 degrees.
This year's chassis has had a complete redesign. Moving away from the 1-inch aluminum squared tubing, this year's design weighs 48% less and utilizes 3/4-inch squared tubing, totaling to a final weight of just over 2 kilograms. The welding and powder coat was outsourced to a local fabrication shop, All American Fabrication. Thank you guys for the help.
Our subsystem continues to use the ROS framework because of its flexibility, modularity, and extensive library support. We are also incorporating control area network, CAN bus, to improve communication and modularity between our components and our Rover and onboard computer. Other sub-teams such as Autonomous are able to utilize our nicely packaged nodes and topics into what we call just mobility for their respective tasks.
The autonomous system performs localization by using fused sensor data from our Z2i camera, GNSS, and IMU. This year, we are implementing computer vision algorithms to help with our autonomous tasks.
When navigating a specific region of interest, from camera feed is extracted and fed into a custom algorithm that determines and projects the rover's path. We trained the YOLO model to detect bottles and mallets in the environment, and the same model is being extended for the obstacle avoidance part that is going to be a crucial part of the path planning.
We continue to use OpenCV's Aruco Detect library for Aruco tag detection, and custom ROS packages are used to integrate the model's outputs with mobility.
This year, the team decided to design 2 different end effectors, a parallel effector and a 3-finger end effector. Having 2 different end effectors will allow the team to achieve better results during the extreme delivery and servicing mission by choosing the best end effector for the mission tasks. The 3-fingers end effector was designed using a worm gear configuration to have a greater output torque and a fiber mechanism for a better range of motion for each finger.
This year, we went with a parallel arm mechanism in which both the shoulder and elbow's motion were independent of each other. In addition, through a 4-bar mechanism, both shoulder and elbow are actuated using motors at the base of the arm, preventing the heavy mass and vibration of motors from sticking out at long distances.
For our science system this year, we have implemented a telescoping double box design affixed to rails integrated onto the chest. This operation involves lowering the science system until the lower box hits the ground, which telescopes the lower box into the upper box, revealing the sand auger. The sand auger then rotates to collect the sample. After collection, the science log will be pulled back up and the test tubes are rotated into position. The life detection method employed by our science system entails a hydrogen peroxide test. Hydrogen peroxide is preloaded into the test tubes and upon mixing, reacts with any carbon present to make H2O and CO2, which will be released in gas form.